Welcome to my YouTube channel. I am Acho Francis Deban. Don't forget to subscribe and press your like button. So today we'll be dealing with balancing of redox reactions using oxidation number method. Now, in the course of us balancing our redox reactions, we must be acquainted with the oxidation number, how to calculate our various oxidation numbers, because we'll actually need them in the process of doing that. So, for the sake of those who may have forgotten the oxidation number, how to balance, how to get or determine the oxidation number of an element or a compound or whatever it is. So we will begin with with the determination of what oxidation number first. So in the course of doing that, when we're done with that, we'll go down to the balancing. So let's start with the rules. First, we say the oxidation number, permit me if I have to read that, is defined as a charge which an atom appears to have. An atom appears to have. When electrons are counted according to some rather arbitrary rules, or better say it can be represented as a way of numerical expression, the oxidation state of an element in any of its compounds. So we determine the oxidation state. For example, if I have H2SO4, which is tetraoxosulfuric acid, I will be asking you to determine the oxidation state of sulfur in that compound. Let me give you a practical example. I have H2SO4. This is tetraoxosulfuric acid. According to the rules of oxidation number, which I'm going to read them to you, we say the oxidation number of all elements or compounds in their free state is equal to 0. Definitely, I can now equate this to 0. And now, I have to know what is the valence state of hydrogen, of oxygen, in the course of my determining what the oxidation number. So I will say hydrogen is 1, so it's 1 times 2. 1. Then plus sulfur is what I'm looking for, plus oxygen is minus 2 times 4. It's equal to 0. But now, the question is, how do you know, or how will you know that hydrogen is 1, that oxygen is minus 2 and not minus 1, that the halogens are whatever they are, potassium is plus 1 or calcium is plus 2? How do you know that? So in our course of us knowing that, I will take us a little backward from the knowledge of, how they call it, the 20th element and the periodic table. So if you remember your 20th element and you also remember a little of your periodic table, we'll be able to fix that appropriately. So let us go a little backward before we can get down to this. Now, I want to determine the oxidation state of potassium, or the valence state. We call that plus 1. We say potassium is plus 1, but how will I know that it is plus 1? Then we go. We say potassium in its electronic configuration, or the atomic number, is 19. So we say this is potassium, atomic number is 19. We go to our electronic configuration process, the old method, which is 2, 8, 8 plus 16, 17, 18. 1 will give us our 19. This is the old method of determining what the electronic configuration of potassium. Which means we can easily say potassium have, in the first share contains 2, in the second share contains 8. Now in the last share, in the third share contains 8 again. And in the last share it contains 1. Now, from here we can now determine the group in which potassium belongs in the periodic table, and even the period when the case arises. So it has 1, 2, 3, 4. It has 4 shells. It is found in period 4 in the periodic table. And it has 1 electron in its outermost shell. It is found in group 1. So, for me not to be doing this whole thing, you can easily look here, 2, 8, 8, 1. 1, 2, 3, 4. 4 shells. So it says shells 4. Group. The last one in the outermost shell is 1. Therefore, potassium belongs to group 1. Period. Period 4 don't show. It has 4 shells. Then period 4 of the periodic table. So that's potassium. So the valence state of potassium is +1. So if I want to determine my compound, let me say potassium whatever, that potassium now has oxidation state of 1. I don't need to go far. Now, if I have calcium, for example, let me take out this, I'm done with this. Calcium is 280, atomic number is 280. So this is my calcium, 280, that's 2882. Calcium is found in, it has 4 shells, which is period 4. And it has 2 electrons in its atomal shells, which means group 2. So the valence state of calcium is +2 because the number of electrons in its atomal shell is +2. And so on and so on. Magnesium 2 is 12. Let's take magnesium 12, which is 282. It is in period 3, group 2. So the valence state is +2. Aluminium. What is the atomic number of aluminium? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminium. That's 13. So now, if we have our aluminium, which is 13, this is 283. It is found in period 3, 1, 2, 3, because there are 3 shells, and it is found in group 3 because it has 3 electrons in its atomal shell. So the valence state of aluminium is +3. Now, there are certain other compounds or elements that have variable oxidation state, which means they have more than one oxidation state. Some like sulfur and so on, even carbon, minimum. So those ones, we don't determine them. So any of the compounds we're going to be dealing with must have a vivid word, valence state, which we are going to use in the course of our experiment. So now, what about group 7? Those in group 7, the halogens, all of them have the valency of -1. All the group 6, which is oxygen, oxygen is -2. Sulfur has variable oxidation state, so many times we look for the oxidation number of sulfur in a particular compound. So it is not unique, it's not static, it changes because sulfur has a variable oxidation state. So on and so forth. Now, oxygen, like you will see in the course, when I give you the rules, is always -2 for oxygen, -2 in a normal compound, but in a peroxide, it is -1. So any compound you deal with that is a peroxide, the valence state of oxygen therein becomes -1. But like H2SO4 is -2, magnesium oxide is -2, and so on and so forth. So let's take the rules of oxidation number so that we can proceed further. I will read them. Permit me, just pay attention. Number 1, we say the oxidation number of an uncombined atom or any atom in a molecule of an element has an oxidation number 0. For example, it's uncombined. So if I have H2, the oxidation number of hydrogen molecule here is 0. Sulfur uncombined is 0. Magnesium on itself uncombined is 0. On its own, it is 0. Now, we have oxygen, we have sodium, we have sulfur, phosphorus, all of them in their normal state uncombined with any other element. They are all what? 0. 2. In most compounds containing oxygen, the oxidation number of each oxygen atom is -2. But in compounds like hydrogen peroxide, which is H2O2, the oxidation number therein is -1. 3. In simple ions, these are compounds that have charges in them. In simple ions, the oxidation number is equal to the charge on the ion. So if I have aluminium 3+, the oxidation number of aluminium here is equal to +3. If I have SO4 2-, the oxidation number of this compound is -2. It's equal to the charge on the ion. And so on. We have ion 2+, ion 2+, ion 3+, and so on. The oxidation number of ion here is +2, here is +3, and so on and so forth. We're only explaining, we haven't started here in the calculations. We just have to get acquainted with whatever we're going to be dealing with, so that we'll not be too far apart from the other understanding part. 4. The algebraic sum of the oxidation numbers of all the atoms in an ion is equal to the overall charge of the ion. That is that of the one I just gave you, the SO4 2 minus. So this is SO4 is equal to minus to the overall charge. The algebraic sum, the last one, the algebraic sum of the oxidation numbers of all the atoms in a neutral compound is 0. A neutral compound means a compound that does not have charge in it. So if I have calcium triiodocarbonate 4 in its neutral state, this is equals to 0 to begin with. So if I have HNO3 in its neutral form is equals to 0. H2SO4 is equals to 0, and so on and so forth. So these are the rules. Get yourself used to them. Then with this, we can take our first question. Question number 1. Calculate the oxidation number of manganese in KMnO4. Question number 1. The oxidation number of manganese in KMnO4. We're going to, when we're done, we're going to find out what the name of this compound is. I don't want to tell us right now, but until when we're done. You see why? So if this is the we should find out of manganese in this compound. Now, remember the last rule is the oxidation number of any compound in its free state. Neutral form is equals to 0. So therefore, this becomes equals to 0. Now, what is the oxidation state of potassium? Well, like I told you, it is atomic number 19. It has 2881, which means that belongs to group 1. The valence state is 1. So here, potassium becomes plus 1. Plus manganese is what we're looking for. So let's still write it down. Plus oxygen. We see oxidation number of oxygen. In most cases, is minus 2, unless if it is what? In peroxide, that could be minus 1. So this is minus 2. So I have minus 2 times 4. This is equals to 0. Now, this is 1 plus manganese. Plus times minus is minus. 2 times 4 is 8. This is equals to 0. If I make this the subject, I have manganese is equals to minus 8 crossover become plus 8. Plus 1 crossover become minus 1. So manganese is equals to 7. We always use plus in front of it. So this is 7. So the compound now becomes potassium tetraoxomanganate 7, because the oxidation state of manganese in that compound is 7. Let's take another question. Question to calculate the oxidation number of chromium in this compound. Let me take this out. Question 2. Cr2O72 minus. That is what they gave us. They say we should calculate, what is it? Calculate the oxidation number of chromium in this. Now remember we say the algebraic sum of the charge or the ion in a compound, either compound or whatever, is equals to what? The power, which is what? Minus 2. So therefore I can have this to be Cr2O7 is equals to minus 2. Now we're looking for chromium, but I have 2 attached to it, so this becomes chromium times 2 plus oxygen. Remember, is always minus 2. Minus 2 times 7. This is equal to minus 2. Chromium times 2 is 2 chromium. Plus times minus is minus. 2 times 7 is 14. Minus 2. I want to make this a subject. So I have 2 chromium is equals to minus 2. This crossover becomes plus 14. 2 chromium is equals to 12. Divide both sides by 2. I'll have chromium is equal to plus 6. So the oxidation number of chromium in this compound is what? Plus 6. Alright. Let's take 2 or 3 more, then we'll proceed. Calculate the oxidation number of sulfur in this compound. Let me take this out now. Okay, of sulfur in this. This is 3 iron SO4. Remember, iron could be iron 2, it could be iron 3, but let's see what it is. So we want to calculate the oxidation number of sulfur in that compound. Let's presume it's plus 2, then we'll see what we get. The oxidation number of all the elements in the compound in their free state is equal to 0. So iron here, we take it to be plus 2 plus sulfur, which we are looking for, plus oxygen is minus 2 times 4 equals to 0. 2 plus sulfur plus times minus is minus 8. 2 times 4 is 8. Is equals to 0. So this, I make sulfur the subject, is equals to minus 8 crossover become plus 8. 2 crossover become minus 2. Sulfur is equals to plus 6. So that is iron tetraoxosulfate 6. Obviously iron 2, because we have our valence state of iron to be 2. So it's iron 2 tetraoxosulfate 6. Now let's take another compound. 3. Okay, that's 3 already. Let me give you 4. I have Na2S4O6. We are calculating the oxidation number of sulfur in that compound. Now, the oxidation number of all the elements in their free state is equal to 0. So this is 0. So sodium is plus 1, the valence state, plus 1 times 2 plus sulfur is what we're looking for. So sulfur times 4 plus oxygen is minus 2. Minus 2 times 6 all equals to 0. Now this is 2 plus 4x minus 12 equals to 0. Plus times minus is minus. So make this, I have 4s. This crossover become plus 12. This crossover become minus 2. 4s is equals to 10. Am I right? Yes. Divide both sides by 4. Cancel this. I have sulfur is equals to 2.5. Let's proceed. We'll solve like 3 more before we move on. Let's take another one. Calculate the oxidation number of sulfur in this compound. We should calculate the oxidation number of sulfur in the compound which I want to give us right now. S2O3 2 minus. Now, we say all of this is equal to the charge, which is minus 2. So I have sulfur times 2 plus oxygen is minus 2 times 3, or is equal to minus 2. 2 sulfur plus times minus is minus, 2 times 3 is 6, is equals to minus 2. Now 2 sulfur is equals to minus 2 plus 6. When minus 6 crossover become plus. 2 sulfur is equals to plus 4. Minus 2 plus 6 is plus 4. Divide both sides by 2. 2. So my sulfur become plus 2. So that's the oxidation state of what sulfur in that compound. Let's take another one. Calculate the oxidation number of nitrogen in this compound. The oxidation number or state of nitrogen in NO3 minus. Remember, whatever we have is equal to the charge. So now I have NO3 is equal to minus 1. The charge is minus 1. Nitrogen is what we're looking for, plus oxygen is minus 2 times 3 is equal to minus 1. Nitrogen plus times minus is minus 2 times 3 is 6 is equal to minus 1. N is equal to minus 1, which is here. This crossover becomes plus 6. N is equal to plus 5. Alright, that is it. Let's take. We should calculate the oxidation number of chlorine in this compound. We're calculating the oxidation number of chlorine there. So everything is equal to minus 1. So let's take it again. This is my chlorine plus minus 2 times 3, or is equal to minus 1. Chlorine plus times minus is minus 2 times 3, 6 minus 1. So chlorine is equal to minus 1 plus 6. Chlorine is equal to plus 5. Now let's take the question that before we go into that one, let's take this other one. Calculate the oxidation number of sulfur in the following compound. Sulfur in this compound. KSH. Alright, yeah. So this, everything in its free state is equal to 0. Potassium is plus 1. Plus sulfur, which we are looking for, plus hydrogen is what? Which is plus 1. So let me just put it 1. All this is equal to 0. 1 plus x plus 1 is equal to 0. Make x the subject. This is equal to this crossover become minus 1. This crossover become minus 1. Sulfur is equal to minus 2. There we go. Let's take, we'll stop a lot. Let's take questions that will introduce the redox titration to redox balancing of redox equation to us.